Greetings and welcome to Tutor. So far we've been learning about list comprehensions and everything. So let's apply that to a very interesting problem over here. So researchers at the Indian Institute of Science last year discovered a very interesting thing. They developed an expression for pi, a new way of representing pi. So these are string theorists from IISc, and this is the paper that they wrote. And there's a lot of math over here. You could go through this. I'll attach the link of this paper in the description. But towards the end, they presented a very interesting formula for pi, which is this. And I'll tell you about this formula, but we'll be trying to compute the value of pi using this particular formula here. And over here, there is this parameter lambda. Lambda is an independent parameter that they've used. And this parameter can be manipulated here and there to get an accurate value of pi. So they mentioned that in the limit of lambda tends to infinity, this summation becomes this, which is nothing but a Madhava series. But Madhava series is considered to be not very accurate for calculating pi, which has been mentioned over here that the series takes about 5 billion terms to converge to 10 decimal places of pi. But this representation is so wonderful that with the values of lambda between 10 to 100, it takes about 30 terms to converge up to 10 decimal places. So let's have a look and see if we are able to compute pi using this series, using the knowledge of list comprehensions that we have so far. So let's go to our Python ideally, spider, and I have uh, imported the libraries for plotting as well as the math library. So the math library we are going to use in order to get the value of pi, the actual value of pi. So let's say p equals to math.py. So this gives me the actual value of pi. Okay. Now let's, using the series, let's try to compute the value of pi. So over here, let's go back to our series. So first, we'll be trying to compute this summation over here. So let's first of all write the jth term of this particular summation, right? So let's write jth term of the summation. So I'll just, I can't copy this to my ideally, but I could just come back and forth here. So 1 upon j factorial, we are calculating the jth term. So I'll write it step by step. So jth term of the series is 1 upon j factorial. And to get the factorial of a number, you can use the math module. So math dot factorial j, this gives us 1 upon j factorial times 1 over n plus lambda. So 1 over n plus lambda is, so it's the jth term, so 1 over j plus lambda is an independent variable. So we'll just say it can be anything from 10 to 100 as we saw in the paper. So let's just say it's some I. We'll assign this value of I to lambda, right? And minus 4 upon 2i plus 1. Sorry, 4 upon 2j plus 1 because this is jth term. So 4 upon 2j plus 1. So this is the first bracket. After that, the second bracket is this. So, but more importantly, this actually is a product. So this subscript n minus 1 is actually known as a Pochhammer symbol. Pochhammer, I'm not sure what's the pronunciation, but basically it's a symbol which is written in order to get a product. So for example, if I write 5 underscore 3, which is underscore means the subscript in this case. So 5 subscript 3 is actually 5 times 6 times 7. And if I write 5 subscript n, that is equal to 5 times 5 plus 1 times 5 plus 2, and so on till 5 plus n minus 1. So that is why when n was 3, so we went from 5 times 5 plus 1 times 5 plus 3 minus 1, that is 2. So we'll go on till n minus 1. So this is again a product. So let's try to compute this bracket separately. So this bracket, we'll say is, so the first term of this bracket is just 2j plus 1 squared by 4n plus lambda. So let's write the second, that bracket over here. So it's 2j plus 1 whole squared over 4 times j plus lambda. So 4 times j plus lambda we've called I minus j. So that gives us the first term of this. And then we'll say this is this plus k, and we'll save the entire thing in a list for k in range, and k goes from 0 to n minus 1 in this case, and n for us is j, so it has to go from 0 to j minus 2, because so I'll just repeat what I said. So if I'm writing 5 underscore n, that goes till 5, 5 plus 1, and so on till 5 plus n minus 1. So I have over here this bracket with n minus 1 in the in the subscript. So this will go as whatever is this bracket over here, this bracket over here, times this bracket plus 1 times this bracket plus 2 till this bracket plus j minus 1. So, sorry, this bracket till j minus 2, because there was n minus 1 in the subscript. So we wanted to go till j minus 2. So we'll write j minus 1 here, because the last term is not j minus 1. It's going to be j minus 2 in the range. So this is the entire list of these terms. And then we can just get the product of the entire list using math.product. So the application of list comprehension over here. After that, this entire product has to be multiplied to this thing. So we've multiplied it. So now we've got everything. We've got everything. This computes the jth term of this entire summation, right? And after that, we have to sum it from n equal to 1 to, we are going to sum it for 30 terms. So let's see what happens. So let's just say n equals to 30. So we have to sum it for n equals to 1 to 30. So we'll make a list out of this, right? And we'll say for j in range, n goes from 1 to 30, which is n, basically. So n plus 1. So again, it will compute till n, and the parentheses gets closed. So this is my list over here. And after that, I will compute its sum. So I've got the entire list, and now I'll compute the sum. So that is what we did in list comprehensions. If you remember, we first made the entire list. And then if we don't want to store the entire list, rather we just want to calculate the sum. So we would use the sum function over here. So that can be done. And we've got this one line summation over here, rather than doing a lot of complex coding. We've just written it down in one line. That is why it is called as a list comprehension. Now we have to take lambdas from uh, 10 to 100. So let's say lamb, we are making a list again, is equal to I for I in range 10 to 100. So 10, 101. That gives me a list of lambda. And then I have to iterate over all possible values of lambda. So I'll just make this up into a list once again, right? For I in lambda. So remember, we had assigned the variable I to lambda, and now lambda itself can have values from 10 to 101. So uh, each element in the list corresponds to a single value of lambda, right? So the first element, for example, corresponds to lambda equals to 10, the summation corresponding to lambda equals to 10. Similarly, the second element would correspond to summation at lambda equal to 11, and so on, right? And yeah, and this is not pi, this is pi. 4 plus this summation, 4 plus this summation is pi. So now we have got a list that is basically the values of pi corresponding to different parameters, different values of lambda. So we'll say pi equals to this, or yeah, pi equals to this. And now let's just see what are these values of pi. So I'll just plot this. So plt dot plot lambda comma pi. So I'm seeing what values of pi I'm getting for different values of lambda, right? And let's go with that. So if I run this, I have got the summation over here. And as you see, the plot over here shows me pi in the y-axis and lambda values in the x-axis. So this is 3.141592653 plus this number into 10 to the power minus 11. That means uh, it is, let's say, this entire thing plus some 5 into 10 to the power minus 10. That is what we've got over here. So this is, of course, the value of pi that we've got up to a certain digits. But let's try to get the errors. So one way to get the errors is using relative absolute errors. So relative absolute errors are calculated by calculating the absolute value between whatever we've calculated and whatever we know actually. So if we've calculated pi, so let's say k minus whatever the actual value of pi divided by p, the actual value. So it's calculated minus actual over actual. That is known as an relative absolute error. And then we'll evaluate this for all pi's. So for k in pi, and let's say that is my error. So we've got the list of errors. So now let's plot the errors rather than plotting the absolute value of pi. That will give us a better idea. So if I've just run this line of code, I've got these errors. And as you see, my errors are of the order of maximum error that I could see here is of the order of 2 into 10 to the power minus 11. That means I have been able to compute pi correctly up to 10 decimal places, which is what the paper did claim, that to converge to 10 decimal places, the new term, the new representation that just takes about 30 terms. So that's really cool. That's a very cool way of representing pi. And yeah, you could do similar cool things, but I want to just emphasize on how wonderful list comprehension is, that we managed to calculate a product of multiple terms we managed to calculate a sum of multiple terms, and we managed to calculate this entire list for so many values of lambda. And all of this complex math, all of this complex series calculation, we managed to do just in a single line. So, as we have written in this paper, similarly, just in one line, we've been able to write pi. Similarly, over here, we've been able to write pi in just a single line. So that is how powerful list comprehensions can be. So this is a very nice way of being able to write your codes. This makes it very concise, and you're very easily able to write codes on Python without making it very complex. So yes, that is all for today. Thank you.